All right, guys, we're back to go over the examples for section 12.1 of Newton's law of universal gravitation. So example 12.1 is pretty much as straightforward of using this as you get, but let me kind of relate it to simulation as well to better visualize it. First, look at the example from your textbook. This is on page 386 of your online text. It says the mass m1 of one small sphere in the Cavendish experiment is 0.01 kilograms. Remember, you were to watch the Cavendish video at some point to understand what that experiment was. All right, but m1 is 0.01 kilograms, and mass 2, the largest sphere nearby, is 0.5 kilograms. The center-to-center distance between the large sphere and the small, that would be the R value, and the formula is 0.05 meters. Find the gravitational force F sub g on each sphere due to the nearest other sphere. Remember, another thing I'm going to say again is that once we define Fg as a more general force due to gravity just between any two objects, we do not call it weight anymore. Okay, we only call something as weight when force of gravity and weight is the same thing when one of the masses is an object on or near the surface of the planet or moon or whatever that it's on. This is a more generalized thing, remembering about the force between two masses in the universe, which could be illustrated in this little simulation. So in this case, they're planetary. So here's the mass of the moon, for example, and some planet, which may or may not be Earth. All right. There's a gravitational force of attraction between these two. And if I change the mass of the moon to up it, then you can see in the top right-hand corner, the force goes up. If either of the masses grow, then the force grows. Right? So there's a direct relationship between M1 and M2. If they go up, the force goes up. If the difference in distance between them, you can see the further apart we get, the force goes down. The closer we get, the force goes up. And it is an interactive force. So whatever this force is between the two masses, whatever it comes out to be, it's the same on both masses. That'll be an interesting thing to look at when we look closer into orbits, which is coming in this chapter. All right, we'll kind of point out that feature again. But the main thing is, if we figure out through this formula, the force, let's use this number right here, is 35.5 newtons between the two objects. That means each object is feeling that force equally. It is an interactive force that follows Newton's third law. For every action, there's an equal and opposite reaction. Okay, so with that in mind, let's go back to solving the example that we just looked at. So I just simply listed the two masses, their distance apart, and using big G found in Cavendish, 6.67 times 10 to the negative 11. We pop all that in, run the numbers, and the force between the objects is extremely small, 1.3 times 10 to the negative 10 newtons. And it should be small. We have two relatively small masses in the grand scale of the universe. Those are very tiny masses. And even though pretty close together, it really doesn't matter since their masses are so tiny. There is not much of a force of gravity between these two objects. However, Cavendish cleverly figured out a way to measure this very small force directly in order to figure out this constant. And by the way, 6.67 times to the negative 11th is a universal constant. That means anywhere in the universe, this constant holds true. Not on Earth or anywhere, really anywhere else, that is a universal constant. That just plugs in the formula. So anyways, the final answer is 1.33 times 10 to the negative 10th newtons. Doesn't really get any easier for that. It's just kind of all plug and chug on that problem. Let's now look at using this formula with other older ideas. So let's go into example 12.2. Okay, so suppose one large sphere and one small sphere are detached from the apparatus in the prior example and place 0.05 meters between centers from each other at a point in space far removed from all other bodies. Yeah, the reason why they're saying that is so no other forces of gravity have any significant effect on them. What is the magnitude of the acceleration of each relative to an inertial system? All inertial system means their own closed system, those two masses with nothing else in mind. So what we would do to figure out this acceleration is go Newton's second law along with the force we just figured out, right? So what we're basically pretending right now is that we're in some system where, we're ignoring any other masses. The only thing gravity being created is the gravity between these objects. There's no other object to consider. So this is the only force. It is the net force. Remember that? Second law, net force, sum of forces. So this force becomes a net force, and net force equals A by Newton's second law. So the acceleration, though, is not the same on both of them. The force is the same, but the acceleration is determined through the second law based on how massive each one is. So if we just apply Newton's second law with that same force to each individual mass and solve for A, object 1, mass 1, will have an acceleration 1.33 times 10 to the negative 8th meters per second squared. And object 2, since it's has a different mass, will have a different acceleration. So plugging it in mass, its acceleration is not as great, 2.66 times 10 to the negative 10 meters per second squared. And that should make sense. If these two are both experiencing the same force, the lighter object will accelerate greater towards the heavier object, which will accelerate less. And again, this actually has this idea has a lot of concept in it regarding orbits. Just throwing it out there now, we'll study this more later. This is why smaller things orbit larger things and not vice versa. They might have the same force between them, but the less massive object is going to accelerate much more to that force because of the lower mass. Kind of like what's happening here. Like, for example, the moon orbits the Earth because the moon's mass is much smaller than the Earth's. Therefore, even though the force is the same in both of them, it seems like it affects the moon more because its mass is lower. Again, we'll talk about more later. All right, and finally, let's go into the system where we might have to use a little bit of vector math. This would be example 12.3, so it should be bad. Let's put a system where there's not only two masses, but three, because obviously there's all kinds of masses around affecting each other and needing resultants and things like that. So example 12.3, it says many stars in the sky are actually systems of two or more stars held together by their mutual gravitational attraction. The figure to the right shows a three-star system at an instant when the stars are the vertices of a 45-degree right triangle. Find the magnitude and direction of the total gravitational force exerted on the small star by two larger ones. So here's the small star at the origin of our axis in the diagram, and we want to find the force due to gravity exerted on the small star by these two combined. Okay, so we can see some distances apart and figure some out as well. So matters for each of our calculations is really, since we're talking about all in a small star, this one here and this one here, then we're going to have to do a resultant. So let's go over to the work, and I have a similar diagram post the work. So based on, since this is a 45-90 triangle, and we knew the given distance here to here and here to here, we could use the Pythagorean theorem to get the hypotenuse distance from here to here. All right, so we're going to first figure out the force of attraction between just the small one and the larger one up here. That's the work done right here. We're going to call that force 1. All right, that force of attraction. And we're finding on this from the big star on the small star. So it's going that way. So we just use Newton's law of universal gravitation with those numbers and the 2.8 times 10 to the 12th distance. Pop them in, and F1 is 667 times 10 to the 25th newtons. Do the same thing for, I define as force 2, which would be between these ones using the distance of 2 times 10 to the 12th. Plugging that all in, F2 is 1.33 times 10 to the 26 newtons. So this small star is feeling the effects of both of those forces. We find the resultant using vector math like always. I use component method, as we've done this many times throughout the year. I'm not going to go through every step, but using component method, here's all the work right here. Once we get through component method, we could use the Pythagorean theorem, find the resultant force, and the resultant force magnitude comes as 1.87 times 10 to the 26 newtons. And we could also find the angle at that point to represent the direction, and that would be 4.6 degrees. So this represents the force and direction of the combined pull of the two larger stars on that smaller star. And that's it for all the examples in this section. There'll be some assignments posted on it.